point particle can be used to a good approximation as an idealized model of a macroscopic body if these two conditions are met. The first condition is that the characteristic scale of the problem that we are trying to study is much larger than the size of the body. Then we can effectively neglect this size and consider it to be zero. So we treat the body as a point particle. The second condition is that we should be able to ignore in this problem, because it is irrelevant, the internal structure of the body. If these two conditions are met, really we can use the particle model with very good results. And for instance, we can treat planets as point particles and find their orbits with a very good approximation. If we want a better approximation, then we have to take into account that they are bodies with a finite size, and that the sizes are irregular, and then we can only find a much better approximation to these orbits if we take into account those effects. So we would like, the particle model is very convenient because it is kind of universal. It can be used in many instances as a very good approximation. We would like also another universal model that can be used in many instances as well. To find this model, we have to take into account a very important point, which is that in special relativity and in general relativity, rigid bodies are impossible. Rigidity implies the existence of signals transmitted at infinite speed across the body of these rigid objects. You just have to take into account that if one side of the body moves, the other side of the body, it doesn't matter at which distance it is, how big is the body, moves instantaneously, in the same direction. This is what rigidity means, and then it means that the signal that one side of the body has moved is transmitted to the other side at infinite speed. This is impossible, and then rigidity is impossible in special relativity. Taking this point into account, one arrives to the idea of the fluid model. In the fluid model, a macroscopic body is thought of as composed of small volumes, which are called fluid elements. These volumes of matter are very small compared to the size of the body, but on the other hand they are large enough so that we can ignore that they are made of a lot of atoms, molecules, and particles, so we can ignore the internal structure of these fluid elements. Then each of these fluid elements is characterized by magnitudes which are local averages. So for instance, one can talk about the local mass density. So at a given time, at a certain position in the body, there is a certain density of mass, and if we refer to a point, this means that we are taking the average in a local region around that point. Another quantity that can be used to characterize this fluid is the pressure. Again, at a time and a given point, it will be a local average over a region. This kind of pressure is called isotropic pressure because it is the same in all directions. This is why it is characterized by just a scalar number. And another important magnitude that will characterize these fluid elements is the velocity. This is in the Newtonian case or non-relativistic case. In the relativistic case, we will use this velocity or for velocity. There are other quantities that can be used to describe the fluid, like the temperature, entropy, viscosity, and so on. And all of them are really described as they are fields, because they tell us at each point and time what is the value of the corresponding magnitude. So effectively we have a fluid is a continuous medium, which these volume elements can move, and so this medium can flow. This flow is the result of the organized motion of the different fluid elements. This is a description which is of universal applicability or a very extended applicability, just as thermodynamics, as long as the conditions under which it is a good approximation are met, just as in the case of the point particle. Okay, if we take into account all the possible variables that can characterize these fluid elements, the description of fluids becomes very complicated. So one starts by an idealized version of these fluids, which are characterized by only these three quantities. Okay. These fluids are called perfect fluids. Okay, and we can study them in the context of Newtonian physics or relativistic physics. So we are going to start by the Newtonian case. So Newtonian perfect fluids. Okay, they are governed by the following four equations. First of all, the continuity equation. Perhaps I didn't mention this when we talked about conserved currents. Remember in the relativistic case how this equation, which is a time derivative plus divergence, a spatial divergence equal to 0, can be used to express the conservation of a charge. There is a charge density and there is a flux of this charge, and this is the local version. When you integrate this formula, it translates into a conservation law that tells you that the charge that is enclosed in some volume is equal to the, at a given time, is equal to the charge that there was at the beginning, plus all the flux of the charge that has entered this volume minus the flux of the charge that has exited this volume. This is what the conservation means. Here this continuity equation has exactly the same structure, and here the density that appears is the mass density, and the current will be the matter density current. So J0 will be replaced by rho, and Ji will be replaced by the mass density multiplied by the velocity. And indeed, there are no speeds of light here at any place, and we just have this. You see that it has exactly the same structure as this equation that we studied in the context of the Noether theorem. Okay, it just expresses that the mass is conserved, just as this equation expresses the conservation of whatever charge is involved. There is a particular case that one considers sometimes, which is what is called an incompressible fluid. So this is a perfect fluid whose mass density is always constant. Doesn't matter what the pressure is, whatever, this rho does not change. If it doesn't change, then the derivative with respect to time is 0, and rho can come out of this derivative, and you just have as a consequence that for an incompressible fluid, the divergence, the spatial divergence of the velocity is 0. And remember that this is the velocity of for certain fluid element, and this is a field. Okay, it's a field of velocities. The second condition that controls the behavior of a perfect fluid is the Euler equation. Okay, this is a very important equation, and let's write it first, okay? And then we explain exactly how it works or how it can be argued that it has this form. So it is partial vi partial xj equal to minus 1 over rho partial p over xi plus fi divided by rho. Okay, what is Fi? Fi is the density of external forces. Here in these equations everything is a density. So density of external forces. So for instance in hydrostatics so hydrostatics means that the velocities are zero. Okay, the fluid does not move, and the density of forces are just the forces of the gravity. So it's the density of mass times gravity. Okay, and if you plug these conditions into the Euler equation, you arrive to just rho pi equal to dpi over dxi. This is the equation, or one of the equations, that governs hydrostatics, the equilibrium of fluids. Okay, so what is this equation? If the continuity equation expresses the conservation of mass, this equation expresses or is equivalent to the Newton's second law of dynamics. But applied to the particular case of fluids. So in order to explain how one can arrive from Newton's second law to the Euler equation, we think on the dynamics of a volume element of fluid, one of these fluid elements, and how it should move. So we know that the Newton law tells us that the variation with respect to time of the momentum per unit mass, so this is density of momentum, will be equal to the force per unit mass. This is basically Newton's law, but per unit mass. And this force per unit mass will be the force per unit volume divided by the mass density. Just check the units to be convinced that this is true. And okay, the force per unit volume is minus the gradient of pressure. There is pressure plus the density of other external forces. Pressure, if you want, is a force which is internal of the fluid. So we just consider the density of external forces here. And everything divided by the mass density. This is going to give us d vi over dt equal to minus 1 over rho. This is the division, so the gradient of pressures minus density of external forces. Now this time derivative is a total time derivative, so we have to take into account two things in order to do it. First of all, that Vi has some direct dependence on time. But second, okay, because we said that the Vi is Vi of t and x. But secondly, that there is also some dependence on t because the volume element, which is at the position t, x, also moves. So there is some dependence on t derived from the fact that this x moves. Let's say it like this. So the derivative with respect to time, in general, we'll have two components: the partial derivative with respect to t plus the derivative of the xj's, or with respect to time. These are the velocities, and like this is just like the chain rule. That we do this all the time with Lagrangians. Okay, so it's just exactly the same thing. So now this applied to be Vi. Okay, and by doing this, we just recover the Euler equation that we wrote above. A third equation that governs the behavior of a perfect fluid is an equation that expresses the absence of heat transfer between different fluid elements. So if we call S the specific entropy, so it's entropy per unit mass, then S must be constant along the flow. So ds dt, which is by using this sign formula here, Vi partial S partial xi is equal to 0, although we will not use this equation much. Okay, and this, you can say that this is an expression of the second law of thermodynamics in this context. So finally, the fourth equation that governs a perfect fluid is an equation of a state for the fluid. Okay, this is a property of the each particular fluid. Okay, and it is a function that relates pressure and density, in this form. Okay, or you can also express it as function P as a function of rho. Okay, let me mention one particular case, just as we mentioned the incompressible fluids, as fluids for which rho is constant. There is a kind of fluid that has zero pressure, and zero pressure, a fluid with zero pressure is called especially in the astrophysical context or cosmological constant, is called dust. It is incoherent matter. And indeed, there are bodies or fluids that really adapt to this description in some approximation. Okay. Now, an interesting thing is that some of these equations that we have written can be combined into a set of equations. If you want a tensorial set of equations, just like the four Maxwell equations can be combined into, or two can be combined into the Maxwell equation partial mu f mu nu, okay, and the other two can be combined into the Bianchi identity, as we have seen. So We can combine several of these equations into a more compact form using something called the Newtonian stress energy tensor. Okay, that we will write Ti, and in some places is denoted by pi ij. Okay, and this stress energy tensor, similar to the energy momentum tensor, describes energy and momentum. So okay, let's take this. Let's consider the density of momentum of the fluid, okay, which is rho vi, and let us compute its variation with respect to time, the partial derivative with respect to t, and let me call this already, okay, I will define it as minus t0i. Okay, you see that the Newtonian tensor only has components ij, but we'll extend it to a full 4x4 tensor later, and this will be the components t0i. So this is the partial derivative of rho with respect to t times vi plus rho, the partial derivative of vi with respect to t. So now I'm going to use the continuity equation to replace the rho by the of rho vi and the divergence of the rho vi, and the Euler equation to replace this, the Euler equation with Fi equal to 0. Otherwise, there will be no conservation of momentum. So for the moment, this is what I'm going to use. And here I have minus the rho. I have to use the index j because vi is already here, and here I have rho times, now let me look into the Euler equation. I have this in the right hand side, so minus vj dvi dxj, and then the right hand side of the equation, which is minus 1 over rho dp dxi. Okay, now see that these two terms combine into a derivative minus the of rho vj vi dxj, and here the rho and rho cancel, and this is minus dp over dxi, which I can write as minus the derivative with respect to xj of rho vi vj plus p delta ij, because this delta will convert this index I into the j that I have here, and I am going to define this as minus tij. Okay. Furthermore, I'm going to define minus T00 as the mass density. And with these definitions, okay, then I construct my energy momentum tensor. This minus sign is conventional, okay, because you know that in my conventions energy density is minus T00, so here this is why I put the minus here. So I have rho vj, rho vi, and in this box I have rho vi vj plus delta ijp. Okay, this is the Newtonian energy momentum tensor, but you see that it is part of a larger structure, which arises completely naturally. Now, the virtue of this definition is that if you compute the divergence, okay, this covariant divergence, this is a continuity equation, of course, okay, and set this equal to 0, you recover the continuity equation. Okay, you can just check it. Basically, this is what we have done in this calculation, and if you compute the mu I, set it equal to 0, you get a combination of the continuity plus the Euler equation with Fi equal to 0. Okay, so you could recover from this combination the continuity equation and the Euler equation separately. Okay, and this is interesting because you see that the conservation of this Newtonian, well, of this stress energy tensor gives you the equations of the fluid. Now, we want to do the same really in the relativistic setting. It is almost there, but here all the quantities that we have used are non-relativistic. But before we do that, let's see, just for completeness, what could be the imperfections that modify this perfect fluid and how they are taken into account. First of all, even if it is imperfect or there are other effects that have not been taken into account, it is clear that the continuity equation should always hold in non-relativistic physics. Okay? The mass is conserved in non-relativistic physics. In relativistic physics, it is not, but for the moment we should assume that it is conserved. Then it is only the Euler equation that can be modified. And all these modifications take into account effects like viscosity. They can be expressed, for instance, by modifying the Newtonian stress tensor. This is one way of incorporating them. For instance, you can take a look at chapter 2 in the Landau and Lifshitz book on fluid mechanics. And one of the most popular cases is the one in which these imperfections are taken into account by incorporating two viscosity coefficients, which are called eta and z. And that modify, they control the modifications of the Euler equation. Okay, so the Euler equation, taking into account these viscosity coefficients, takes this form plus Vj. This right hand side is not modified, okay, because it is just the total derivative of the velocity. And the right hand side, of course, this is still here because this is a source of densities of forces, but then there are additional effects and which are internal. This is without considering external forces. Okay, one of them takes into account this is proportional to the second derivatives of velocities. So, and there is a combination of these two parameters, viscosity parameters, which is proportional to a another term, which is a second derivative, but now with a different index structure. So now the free index I, sorry, here there should be no, this is correct. So there is di, which is the free index, instead of being here, it's here. Okay, this equation is known as the Navier-Stokes equation, and well, there is a lot of work on this equations because they are extremely difficult to solve. This is just for curiosity and completeness, but because we are only going to consider perfect fluids. They give us a lot of physics, a lot of interest in physics, and they describe very well, for instance, the universe and many other situations. Now let's go to the relativistic case in the next video.